Okay, here we're told we have a gaseous fuel being fed steadily from a tank to the atmosphere through a converging nozzle. And let's go ahead and just sketch out what that looks like. So here's our tank. We have a converging nozzle. And a young engineer comes to you with the following scheme. Pressurize the tank to a pressure considerably higher than atmospheric pressure. At the fuel nozzle outlet, the Mach number will be equal to 1, so it's choked. And as long as the Mach number is 1 at the nozzle exit, we'll have the same mass flow rate. So do we agree with this engineer, or do we send him back to the drawing board? Explain your answer. So it is true that if the tank stagnation pressure is much larger than the back pressure, so if P naught is much, much larger than P atmosphere, then the flow will indeed be choked. The way we check to see whether or not the flow is choked is we check to see if the back pressure, which in this case is atmospheric pressure over P naught, if it's in fact smaller than or equal to P star over P naught, then the flow will be choked. And if the flow is choked, that means the Mach number at the exit or the throat will be equal to 1. So that is indeed true. And when the flow is choked, then the mass flow rate will be the choked flow mass flow rate, which I derived in a lecture. But let me just write out the formula here for you, just so we have it. You can find this on the formula sheet. So when the flow is choked, this will be the mass flow rate. And of course, P naught is the stagnation pressure inside the tank. T naught is the stagnation temperature inside the tank. A star will be the area at the exit. And it's A star because the Mach number at the exit is equal to 1. Right? So you might be thinking, well, in fact, if the flow is choked, then the mass flow rate's the choked flow mass flow rate. Possibly, so what the young engineer is thinking is possibly then that the mass flow rate will be a constant. That's not exactly true, however, and the reason for that is because the stagnation pressure and stagnation temperature would in fact change inside that tank as it discharges. And you can see that by applying conservation of mass to a control volume that surrounds the tank. So if I just did a control volume that surrounded the tank and wrote out conservation of mass for that, what we would get would be the following. Time rate of change of mass inside the tank would be equal to minus the mass flow rate out of the tank, right? And then the mass inside the tank is going to be related to the stagnation pressure and stagnation temperature. So the mass in the tank would be equal to the density inside the tank, which would be the stagnation density times the volume of the tank. The stagnation density, just from the ideal gas law, looks like this. So you see then, for example, that the stagnation pressure, if I just rearrange this, will end up looking like well, let's see, did I do that right? No, sorry, I did a little math mistake there. So you see, for example, the stagnation pressure would change as the mass inside the tank goes down. So as the mass in the tank decreases because you're removing mass, you can see that the stagnation pressure would change, right? I guess we didn't state exactly what happens to the stagnation temperature in this problem, but if we had a heater and held the stagnation temperature constant, then you'd see the stagnation pressure would decrease. If we said there was no heat transfer, that it was an adiabatic process, then you'd have to write out the first law for the stagnation temperature, but you would find that it would decrease there as well. And if the stagnation pressure changes, then you can see here, for example, the mass flow rate is going to change, or if the stagnation temperature changes, this will change. So the answer ultimately is we don't agree with the young engineer, and the reason is the mass flow rate is not going to stay the same. Even though the flow is choked, the mass flow rate is going to change as mass discharges out of the tank because the stagnation pressure and temperature could potentially change as it's discharging. Now, if the tank was really, really large, then it would be effectively constant because it would take a while to see any appreciable changes in the stagnation pressure as you decrease mass from the tank. So if it's a really large tank, then the engineer is not too far off from being correct. But if it's a smaller tank, you'll start to see changes in the stagnation pressure pretty quickly. All right, we'll go ahead and end the example there.